Hello guys, today we're going to learn about twisting couple on a cylindrical rod or wire. Okay, and we will also learn about angle of twist and angle of shear here. So let us consider a cylindrical rod of length L and radius R, whose coefficient of rigidity is eta, as shown in figure. Okay, uh, then the upper end is fixed while the lower end is free to move. This end is fixed and this end is free to move in anti-clockwise direction. So twisting couple is applied in lower free end in anti-clockwise direction in a plane perpendicular to the length of rod. So if you imagine a plane which is perpendicular to the length of rod, or we can say the axis of rod. Okay, the axis is this one. So uh, if we consider a plane which is perpendicular to this axis, okay, so we move or we twist the lower end in anti-clockwise direction in that direction in which a plane perpendicular to this axis. Okay, you can see the figure clearly looks like this. Okay, so this is the whole cylinder, this one is the axis, and when we move the thing we'll get angles. Okay, and I will talk about it. The length is L, radius is R, and this is fixed end. Okay, and this is the part when you move this thing, like this cylinder, you move this thing like this, and the image you see is like this. Okay, this is the part of the lower end. Okay, and this is the part to show this axis. Okay, when you cut the cylinder, suppose this is cylinder, when you cut it like this, okay, from its middle part. Okay, you will see like this, and we will talk about it. Now, when we apply the twisting couple, each cross-section of the rod rotates about the axis of the rod by an amount proportional to the distance of the cross-section from the fixed upper end. Okay, and now the angle through which any cross-section rotates is called angle of twist. So I'll write about it, this is the important thing. The angle through, angle through, the angle through which any cross-section rotates is called the angle of twist. Angle of twist, and its value is 0 at the upper fixed end and greatest at the free end. Okay, when we look about this thing, this is the upper fixed end, so the angle of twist, which we denote here by phi, okay, will be 0 in this end, while it will be higher in this end. Okay, you see from this figure, when we rotate this thing, this is cylinder. When we rotate the thing, okay, suppose this is cylinder. Okay, this is cylindrical rod, and if we when the upper end is fixed and when we rotate the lower end, it will not act like this. Okay, suppose this is upper end, and when we rotate the lower end, like uh, it will rotate. Okay, but upper end will not rotate, and the angle through which it rotate, you will call it like that will be angle of twist. Okay, the lower end. Okay, now if you imagine this thing, and imagine this is rod, and when we twist it, okay, when we twist it, see we twist it in a anti-clockwise direction here. Okay, when we twist it, this thing will make angle. Okay, see from this part, when we watch from this part, and when I twist it, uh, look, suppose I make a from pencil, I will draw something here. This is uh, okay. So when I twist it, you will see that this moves. Okay, so originally it was here, and it after twisting it comes into this. So this angle at its bottom we'll call phi. We will call it phi, and this phi is called angle of twist. Now I hope you can see this mark I put on the pen. Okay, here is the mark I put on a pen, and when I twist it in anti-clockwise direction, you'll see that originally it was here, and after I twist it goes like here. Okay, so it again makes some angle, and this angle at its surface, okay, it is outermost side. We call it angle of shear. Okay, originally it was here, and when we twist it, it becomes like this. So this angle from here to here, okay, from I hope you are understanding it from here, the mark. Okay, to before twisting and after twisting, the angle that is made is called angle of shear, and we denote it by I here. Okay. Now, as the rod is twisted, a restoring couple is set up in it to the elasticity of the material. In equilibrium position, the restoring couple is equal and opposite, okay, to the twisting couple. In order to find this couple, imagine a cylindrical rod to be divided into a large number of thin coaxial and cylindrical cells, and consider one such cell of radius x and thickness dx. Okay, we already imagine a cylindrical cell. This one is cylindrical cell, a small cylindrical cell, okay, which is divided into large number of thin coaxial cylindrical cell. And this is very small, very thin coaxial cylindrical cell. Okay, just imagine like when you put something like a rod or like some material. When you twist it, the particle, its inner particle also gets distracted. So we are imagining a small inner particle of the rod. Now we will imagine that the thickness of that particle or thickness of that coaxial cylindrical cell will be dx, and the radius of that cylindrical cell from its center over the axis will be x. And before twisting cell of radius x and thickness dx, sorry, before twisting, the rod is, we will let line AB, okay, the line AB is shifted to AB dash. Now here, you can say that this is B, this is B dash, and this is O dash, okay, and this is A, okay, and AB will shift to AB dash, okay, the outer surface, it will shift, okay, AB will shift to AB dash, and so that it, before twisting, the cylinder could be cut along the line AB, okay, and flatten it out, it would form a rectangular ABCD. After twisting, if it is cut along AB dash and flattened out, a parallelogram ABCD is obtained, okay. I will show you. Okay, this is the diagram. Okay, when we this is angle of shear. Okay, I already told you this is point A. This is point A. Okay, so before twisting, if you cut the cylinder, you will get this rectangular ABCD, which is shown by full pencil and full writing or full line. And twist the when we twist the cylindrical rod and cut, what we'll see is we'll see it the B translated into B dash and C translated into C dash. It shift, okay. B and C shift into B dash into C dash, and which will be A, B dash, C dash, D dash, parallelogram, okay. And we will call this angle, the shifted angle, is called the shear, okay. You can imagine, you have to imagine, okay. And now, after we imagine that thing, we call that the twisting component shears the cylindrical shear through an angle BAB dash, B A B dash, which is theta, and this angle is called angle of shear, being maximum for outermost layer, okay, which is maximum for outermost layer and minimum for innermost layer, okay. Just imagine a slice of cake, okay, which has width, or which has say the area for outermost circumference higher in lower end, and in upper end the circumference is lower, or circumference is low compared to the lower end, okay. Uh, this like this type of cake, you know. I will make a figure like this. You can imagine a piece of thing like this, okay. And this angle is theta, and it gets decreased when we go inside, okay. So this angle is called angle of shear. I hope you understood it. So from angle triangle BOPS, okay. Again I will show the figure. See BOB dash, okay. From angle triangle BOB dash, we can write that angle is equal to arc upon radius. So you can see that here B is from up to here and B dash is up to here. But we are imagining that this has thickness very low. So we will imagine that this is arc upon radius, and we'll say phi is equal to arc bb dash upon radius, which is x. Okay, we imagine, just don't forget that r is the radius of cylinder, okay, cylindrical rod, but x the radius of this axis up to the that imaginary coaxial, okay, cylindrical rod. Okay, now uh, when we imagine this thing, we can write that from triangle BOB dash phi is equal to arc BB dash upon f. Again, uh, we can conclude that from this BB dash is equal to xy. Okay, and mathematical term is simple. You can just imagine that. And another triangle we will gonna take is BAB dash. Okay, now BAB dash, we will take two triangle. Okay, we took pi with this angle of twist here, and this triangle. Okay, this triangle, and now we'll take up this triangle. This angle of shear. Okay, we will take two triangles. This is for angle of twist. Now this is for angle of shear, and we will take now BAB dash. Okay, this also arc upon radius. Sorry, yes, arc upon radius. Arc is equal to, oh sorry, angle is equal to arc upon radius. Okay, angle is phi and arc is BB dash and radius is our length. Okay, so from this we can say that from triangle BAB dash, we can say theta is equal to BB dash by L. Okay, from here also you can say theta is equal to BB dash by the length is L. So from this we can conclude that theta is equal to BB dash is yeah, xy. Okay, so xy by L. Okay, yeah, just remember this thing, this topic, theta is equal to x by L phi. Okay, so we were up to here, theta is equal to x by L into phi. So let with the tangential force acting on the base of elementary cylindrical cell considered. Since face area of this cell is 2 pi x dx. Okay, now we already imagined the face area. Okay, now the face area will be 2 pi x dx of the cylindrical cell. This, for this, the face area will be 2 pi x into dx. Okay, x is the radius here, and what we see is surface of face area is surface area is equal to 2 pi x dx, and we also know shearing stress. Okay, shearing stress is equal to force upon area. I hope you know that thing, and force is force and area is 2 pi x dx. Okay, and now we also know that eta, coefficient of viscosity, coefficient of rigidity. Okay, they both are same, but sorry, they both have same thing to denote, but both are different. This is coefficient of rigidity, which is equal to shearing stress upon shearing strain. And shearing stress is, we find out that f by 2 pi x dx. Shearing strain is theta. Okay, that angle is shearing strain. We can say shearing strain is angle of shear also. You know that angle of shear is shearing strain. This will be equals to f by 2 pi x dx. Okay, and 1 by theta. Okay, now on this, since using this thing, we call it abstract or anything, you can say that, and we can use that thing, theta is equal to x by L phi, and the equation will become theta is equal to f by 2 pi x dx into theta is x phi and yeah. Okay, I hope you can see these things. Yes, you can see these things. So from here we can say f is equals to 2 pi by L eta phi x square dx. Okay, so this is another equation, and now we will find moment. So moment of the force will be force into distance, so that will be force into x. Distance is x. Now we can say moment of the force is equals to force into distance. Okay, force into distance, and moment of the force is equals to force into distance is x. Okay, so here distance will be x. uh, Now this perpendicular distance is you can say this perpendicular, this is x. Okay, the force into the distance is perpendicular distance, so here it will be here perpendicular, so uh, this distance is x, so we write here force into distance, that is x. So we already know what is force here. Force is here from here 2 pi eta pi x cube dx. Okay, now when x got multiplied by x square, it becomes x cubed. So moment is equal to, again rearranging the terms, eta pi r cube by dx. So it will be x cube. Okay, this is the couple required to twist. Okay, the elementary cell. This is the couple required to twist the elementary cell of the radius x through an angle phi. Therefore, twisting couple tau required to twist the whole round cylindrical solid cylinder of radius r is obtained by integrating the expression number for 1 between limits x equal to 0 to x equal to r, because uh, the total radius is r. Okay, so integrate it from uh, 0 to r. Okay, so it will be moment, we can call it moment is also equal to tau, which is torque. Okay, and we can say 2 pi eta pi x cube by l dx, and this will be equals to this thing is constant. Okay, so 2 pi eta pi, this eta pi and x cube from 0 to r will be x power 4 on 4 0 to r. Okay, this will be equals to tau s equal to s means the 4 over okay, so this will be equals to 2 and 2 got cancelled, so the result will be pi eta r power 4 to l pi radian. Okay, this will come in radian. Now I hope you are writing it in your copy also, so you can understand it well enough. Mathematics is only understand by mathematics, and all the concepts also you have to write it in your copy so that you can understand it. Okay, without writing you cannot understand, and if you have any confusion you can ask me in the comment box, and now we will do further. So we derive that torque is this much, and the copper required is thus proportional to the twist uh, in radius. Okay, this copper required is proportional to this twist, hence the copper required to produce a twist of 1 radian would be, for 1 radian we'll divide by pi. Okay, so it will be pi eta r power 4 by, we have pi got cancelled out. Okay, so tau s is this, pi cancel out, and remaining term is so now this is CS is the torsional rigidity or restoring copper per unit radiant. Okay, twist. This is uh, when we for the first, for the 1 radian. Okay, the value of torque will be this, and we call this thing torsional rigidity or restoring copper per unit radiant twist of the solid cylinder. And also we can say for 1 radian, which is phi is equal to 1, you can say CS is equal to tau s is equal to pi eta r power 4 by 2 r. Okay, so for now for hollow cylinder we will, for hollow cylinder we will do same process, and up to here, like from up to force. Okay, up to moment, up to copper. Okay, we derive copper is equals to 2 pi eta pi by l x cube dx. Earlier we already have this for hollow cylinder, now we are deriving for hollow cylinder, and we will drag all the things are same up to this thing, up to torque. And while integrating for hollow cylinder, we will integrate from not from 0 to r, but from r1 to r1 and r2 are inner and outer radius. Okay, so we'll integrate up from inner to outer radius, and the thing we will get is you can do it, and the remaining part will be pi eta by 2 pi r2 minus r2 power 4 minus r1 power 4. Okay, everything will remain same like this thing. but only change will be this R. Okay, I hope you are getting a little messy for me, but okay, our mainstream can get it. Okay, so uh, this will be the expression for hollow cylinder. And again, for the torsion rigidity of hollow cylinder, that is C and S for surface total, that S was for not hollow cylinder. Okay, for total, the cylinder which is not hollow, but it's said is flat. And now for hollow, we will denote H or N anything. We want to denote and tau H by phi, which will be equal to phi eta by 2 and phi will be cancelled out. So R2 power 4 minus R1 power 4. Okay, and this will be the expression of torsion rigidity of hollow cylinder. Now we'll drive work done. Okay, this is important. Now work done required in twisting a rod of wire by small angle d phi. Okay, for small angle d phi, work done will be dw is equal to tau d phi. Well, we know that. Okay, tau is forcing distance and work done is also forcing distance. So for small work done, dw is equal to tau d phi. You must know this thing. Okay, torque we can say simply like work done is equal to torque into angle. Formula. This is formula. Okay, so now total work done in the cylinder through phi. Now for phi, for total work done, W is equal to, we'll integrate from here. We can also say that dW is equal to C phi d phi. Okay, yes, tau is C phi. We already know that. What we wrote is C is torsion rigidity. Okay, and it's equal to tau by phi. Okay, we wrote this thing, and from this we can say tau is C phi. Okay, so we use this, tau is C phi. Okay, and we'll write here C phi d phi is equal to C phi square by 2 is equal to 1 by 2 C phi square. Therefore, work done will be equal to 1 by 2 C phi square. And this will be the work done, which is stored in the form of elastic potential energy. Okay, so we have work done, and if you want to write like this whole form, like tau is equal to 1 by 2 C means what is C? This is tau upon phi. Okay, so that will be equal to pi eta r power 4 by 2 okay, into phi square. Okay, this is the whole expression for work done. So this much for this time, and I hope you understood it. If you have any confusion, you can ask in comment box. I will again make another video, and this much for today. So just write it and derive it by yourself. You will understand it more clearly. Okay, thank you.